Hello, everyone. Today we're moving on to Unit 7, which is called stoichiometry. What we're going to be looking at is the impact that math has on chemical reactions. So we'll be studying how much reactants are necessary, how much products are produced, limiting reactants, mole ratios, and more. Today we're going to start off with Lesson 1, which is on mole ratios. So if we take a look at our first slide, it says stoichiometry measures the quantitative, meaning having to deal with numbers, relationships associated with chemical reactions and is used to determine the amount of products or reactants that are either produced or needed in a given chemical equation. You may remember this picture from earlier in the school year when we learned how to do conversions between mass of something and moles of something. We also at that time learned how to go to either molecules or formula units or even atoms, depending on whether we had a compound or a single element. What we're going to be doing now is expanding on this map. If you look at the new map, we're going to take that conversion between mass and moles that we learned earlier in the year and build on that. And in the middle part here, you can see that we're now using the balanced equation to go between reactants and products, and truly between reactants and other reactants, or between products and reactants. The balanced chemical equation allows us to switch what compound or element we are talking about. The best way to explain this is through an example problem. What you'll quickly notice is that we are actually not learning anything new today. In fact, we're taking things that we already know and kind of putting them together like a puzzle in a slightly different form. So if you look behind me, the balanced chemical equation is always going to be our starting point. So the very first thing that we're going to want to do is identify coefficients in our balanced equation. Looking at this equation, the only thing that we'll need to do is to put a 2 in front of our sodium chloride. Now let's double check. 1 barium, 1 barium. We have 2 chlorides, 1 times 2. We have 2 chlorides here, 2 times 1. We have 2 sodiums, we have 2 sodiums. And because carbonate appears the same way on both sides, we can treat that as one thing. We have 1 carbonate over here because there are no parentheses. We have 1 carbonate over here as well. Also notice that this is a double replacement reaction that forms a solid precipitate. So eventually we're going to, especially if you're in accelerated honors, be predicting products and their states of matter. Notice how here we have a state of matter for barium carbonate that's a solid. Now let's take a look at our problem. It says that we have 2 moles of sodium carbonate and we're adding it to an excess of barium chloride. So I'm going to start off here by writing the word excess below this and 2 moles of sodium carbonate here. Calculate the number of moles of barium carbonate produced. Now, in this problem, we are starting off in moles and we're finishing in moles. So this is only a one-step problem. So if we go back and look at our map, we're starting with moles of one thing. We're finishing with moles of another, so we only need to cross 1 arrow. That means we have only 1 step in this problem. So we're going to start off with our 2 moles of sodium carbonate, so Na2CO3. Our 1 fraction is going to be the mole conversion. So in this case, we're going to have 1 mole of Na2CO3 for every 1 mole of BaCO3. These ones are coming from up here. So 1 mole here, 1 mole here. If these were other numbers in our balanced equation, then this ratio would have those numbers in it. We will see examples like that in the future. So obviously, when we multiply this through, we'll have 2 moles of barium carbonate as our answer. And also look at how our units will cross out here. So moles of sodium carbonate will drop out. Let's take a look at a second example. Once again, we're going to begin by balancing our chemical equation. So we have one carbon. We have 4 hydrogen here. So we're going to need to put a 2 in front of water in order to get 4 hydrogen. We have 2 oxygen on the right plus 2 more, that's 4. And here we have an odd number of oxygens. So the only way to fix this when you have an odd number on one side and an even number on the other is to double everything. So we're going to begin by putting a 2 in front. This was a 1, we're going to make that a 2. And this was a 2, we're going to make that a 4. So now let's go back and take a look. We have 2 carbons, we have 2 carbons. We have 3 plus 1 is 4 times 2, that's 8 hydrogen. We have 4 times 2, that's 8 hydrogen. In terms of oxygen, on the right side first, we have 4 oxygen here plus 4 more for a total of 8 oxygen on the right side. Here we have 2 oxygen, 2 times 1, so we need 6 more oxygen in order to get to 8. So on that line, we're going to place a 3. Now let's answer the question. So if we have 3.25 moles of methanol, that's this one right here. We're starting off with moles, are burned in an excess of oxygen. So we have more than enough oxygen. We don't have to worry about that. Calculate the mass of water vapor formed. So we're looking for a mass, which again, remember, is going to be measured in grams. Calculate the mass of water vapor formed from this reaction. So in this reaction, we're starting off in moles and we're going all the way to grams. So if we look at our map, we're starting off in moles here. So we need 1 conversion to get to moles of our product. And then we need a second conversion because we're finishing in grams. So we're going to need 2 ratios in this problem. So I'm going to start off with 3.25 moles CH3OH. Now, since we are in moles, the very first thing that we're going to do is we're going to use our balanced chemical equation to go from moles of methanol, CH3OH, to moles of water. So according to my balanced chemical equation, 2 moles of methanol will give me 4 moles of water. The only time you're going to use the numbers from the balanced chemical equations, the coefficients, is when you're converting from one substance to another, because those numbers tell you the ratio of those 2 different substances. Now, let's take a look at our units. Our moles of methanol are going to cross out with our moles of methanol here. And right now we have units of moles of water. So now we're going between moles of water and grams of water. This is just like what we did back in October and November. Now we're going to use just 1 mole. So 1 mole of water, we would find its mass off the periodic table. So hydrogen equals 1.01 grams per mole. We have 2 of them. And oxygen equals 16 grams per mole. We have just 1 of those. So water has a molar mass of 18.02 grams per mole. So on top, we're going to put 18.02 grams of water. Notice, in each case, I have a number, a unit, and a substance that I'm talking about. Now, more than ever, because we're changing what substance we're talking about, it's very important that we include all 3 parts each time. Notice, number, unit, substance. Number, unit, substance, number, unit, substance, number, unit, substance, number, unit, substance, every single time. Looking at units, our moles of water and our moles of water will drop out. So our final answer will be in just grams of water. Now, plugging into our calculator, we're going to start off here. So we have 3.25. When a number is on top, you may recall this from October and November. When a number is on top, we're going to multiply by that number. When it's on the bottom, we're going to divide. So we're going to multiply by 4 and divide by 2. Then we move on to the next fraction. Ones we don't have to worry about. So in this case, we're just going to multiply by 18.02. Just to drag this out so you can see what I typed into the calculator, we wind up with an answer of 117.13. Now, we're going to be worried about significant figures again. So our answer here of 117 grams has 3 significant figures, and that's based on the 3 significant figures that we started with. Notice, multiply by 4 because it's on top, divide by 2 because it's on the bottom, multiply by 18.02 because it's on top. Dividing and multiplying by 1 does not change your answer, so please don't spend time typing that into the calculator. All right, let's take a look at another example problem. Okay, we're going to begin this problem like we'll begin every problem by balancing our chemical equation. So we have 1 silver here, we have 1 silver, we have 1 zinc, we have 1 zinc. We have 2 nitrates though, 2 nitrates, that's why it's in parentheses. So that means we're going to have to put a 2 in front of silver nitrate. Now that changes the number of silvers that we have. So now we have 2 silvers, so we're going to have to put a 2 in front of our silver on the right side. The rest of these will just be 1s, so we'll put a 1 there and a 1 there. Now let's read through our problem. It tells us in the problem, we start off with 5.63 grams of powdered zinc. So here's zinc, we have 5.63 grams of it. They are added to an excess of silver nitrate solution. So we have more than enough of this. Calculate the number of grams of silver. So we're looking for a mass here in grams formed by the reaction. So in this case, we're starting with grams and we're finishing with grams. So now if we go back and look at our math, if I'm starting with grams, that means I'm starting back here. So I have to make 1 conversion to go from grams to moles. I have to make a second conversion here to go from moles of zinc into our product. And then finally a third conversion to go from moles of that product back into grams. So I'm going to start off my equation by typing or by writing 5.63 grams of zinc. And then I know I need 3 fractions in this problem. In my first fraction, we're going to use the periodic table to go from grams of zinc into moles of zinc. This is no different than what we did back in October and November. So we would look up the molar mass of zinc. That turns out to be 65.38 grams. So I'm going to type in or write 65.38 grams of zinc down at the bottom. In our second fraction, because we're going from moles of zinc to moles of silver, I'm going to use the coefficients from the balanced equation. I'm also going to make them green to show you, to help it stick out for you where we're going to use those numbers. So we have 1 mole of zinc here produces 2 moles of silver. Let's take a look at our units before we go any further. So in our first conversion, we got rid of grams of zinc and we converted to moles of zinc. In our second conversion, Using our balanced chemical equation, we converted from moles of zinc to moles of silver. And now, once again, we're going to go back to our periodic table to look up the molar mass for silver. That will allow us to go from moles of silver into our final product, grams of silver. So 1 mole of silver. Silver has a molar mass of 107.87. Moles of silver will cross out and we'll be left with grams of silver as our final unit. Typing all of this into the calculator. We're going to start off here. We have 5.63. Now, we don't have to enter in 1, so we're just going to hit divided by 65.38. That's our molar mass for zinc down here. Then the next fraction, we're going to multiply by 2. We don't have to do anything with the bottom here, so we can move on to the last fraction. We're going to multiply by 107.87. We don't have to do anything with the bottom because that's just a 1. So we get this as our final answer. So I'm going to drop this down here. We get this as our final answer. We have 3 significant figures here in 5.63. So we're going to keep 3 significant figures here. So 18.6 grams of silver. Remember, if you're confused about significant figures, remember we have no zeros here. So we're going to count all 3 of these. Then here, when we're counting, we're only allowed to keep this place. So we look behind it, because it's a 7, we're going to round that up to a 6. So we wind up with 18.6 grams of silver. Believe it or not, this question is about as difficult as you can get. The process of going from grams to grams, a 3-step process, is as difficult as I can make a problem. So let's take a look at a few of the homework problems that I'm giving you for this week. Okay, let's take a look at some of these homework problems. So we're going to go over problems 1, 2, and 3 together, and then you're going to finish the remaining problems for homework. Taking a look at problem number 1. Again, the first thing that we want to do is balance our equation. So if you notice on the left side here, we have 2 nitrogens. The right side, we currently only have 1 nitrogen, so we're going to put a 2 on this line here. When we put the 2 there, that changes my number of hydrogens from 3 up to 6, because we're going to multiply these 2 numbers together. So that means I need to put a 3 on this line. And then I like to finish it off by putting a 1 in front of the nitrogen, but you don't have to do that. Let's take a look at setting up our equation. In this case, we're given just 1 significant figure. So we're starting off here with 5 moles of nitrogen. So remember, to get the subscript, we're going to hold down Control and hit comma. Now, we want to set this up over 3 lines. So I'm going to go down to the second line, and I'm going to set up my 2 fractions that I know I'm going to need here. So back up to my first line. If I am converting from moles to moles, then the first thing that I want to do here is I want to get rid of my moles of nitrogen. So I'm going to put that on the bottom. So I have, according to my balanced chemical equation, 1 mole of nitrogen. And for every 1 mole of nitrogen that reacts, I get 2 moles of ammonia. Just going to make this look a little neater here. The other thing that I want to do, again, to remind everyone that we are using the numbers from the balanced equation for this part, is I'm going to turn these both blue, just as a reminder that we're getting the coefficients from up here. Okay, for my next part, I'm going to now convert from moles of ammonia to grams of ammonia. So down here on the bottom, and I'll just switch my color back to green, I'm going to have 1 mole of NH3. Now remember, when you're going between grams and moles, it's always 1 mole. The only time that we use the numbers from the balanced equation or when we are changing from one substance to another. So to get the molar mass of NH3, I'm going to type in up here at the top, we have nitrogen, which is equal to 14.01 grams per mole. We have hydrogen, which is equal to 1.01 grams per mole, but we also have to multiply that by 3. So we wind up with a total molar mass for this that is equal to 17.04 grams per mole. Okay, now I'm going to take this molar mass and put it up here at the top. So I have 17.04 grams of NH3. Notice that the 1 mole portion is already on the bottom. Just going to bring that back. So now into my calculator. So I'm going to show everyone that once more. Okay, you can see my calculator and my equation at this point. So we're going to start by typing in 5. And we go to the second fraction here. We're going to multiply by 2. We don't have to worry about the dividing by 1 part. And then my second fraction, I'm going to multiply again by 17.04. So I wind up with an answer here of 170.4. Now, I am limited to just one significant figure. So 170.4, which is going to become just 200 grams of NH3. Bring this back into its spot here. So my final answer here is just 200 grams of NH3. If you're confused by significant figures, please go back to one of our earlier units where we talked about calculations with significant figures and rewatch that video. That should help a lot. Okay, let's take a look at our second problem. In our second problem, we need to once again begin by balancing our chemical equation. So in this case, we have potassium chlorate decomposing to form potassium chloride and oxygen. K and Cl are balanced initially, but oxygen is not. So we have 3 on one side, 2 on the other. This is an instance where we need to find the least common multiple. So we're going to need to put a 2 here in order to get oxygen up to 6, a 3 here to get oxygen up to 6, and then a 2 here to balance out the potassium and chlorides. So in this problem, it says that we're starting off with 10 grams of potassium chlorate, and we're going to moles of oxygen gas. So 10.00 grams of KClO3. Now, when we do this problem, one of the things that we're going to have to do is begin by finding out the molar mass for potassium chlorate. So in this case, we have 1 potassium, so that is equal to 39.10 grams per mole. We have 1 chloride, so that is equal to 35.45 grams per mole. And finally, we have 3 oxygens, so 16 grams per mole for each. Then again, we have to multiply that by 3. So we're going to type this into our calculator. So we have 39.10 plus 35.45 plus 16 times 3, which is 48. So we wind up with an answer, a final answer of 122.55. That has units of grams per mole. So now we're ready to set up our equations. So in our first fraction, we're going to be converting from grams to moles. And then in our second fraction, we'll convert from moles of potassium chlorate to moles of oxygen. So we're going to begin by putting that molar mass on the bottom, so our units of grams will cancel out. And then on top, remember that when we're going between grams and moles, we're always using 1 mole. In our next fraction, we're going to convert from moles of KClO3. So here we're going to use our number from the balanced equation. So we have 2 moles of KClO3. That's from our balanced equation. And on top, we're going to have 3 moles of oxygen, again, coming from our balanced equation. Remember, the only place where you use the numbers from the balanced equation is when you're changing from one substance to another. Otherwise, you're always going to use 1 mole, like we did up here. Okay, typing this piece into our calculator. Just going to drag the calculator to the other side here. So we have 10.00. Now we don't have to do anything with the multiply by 1, but we do have to divide that by 122.55. And then in our last fraction, we have to multiply by 3 and then divide by 2. So multiplying by 3 and dividing by 2, we get an answer of 0.1223902. So I'm just going to copy that. We'll drop that in here. Now, that has far too many significant figures. So in this problem, we're limited to 4 significant figures. So 10.00 has 4 significant figures. So here, our problem can keep 4 significant figures. So if you notice, it ends with a 3, but behind that 3 is a 9. So I'm just going to round that 3 up to a 4 and get rid of all of this. So that is the 4 significant figures that we are allowed to keep. Now we can drop on our unit, which is moles of O2. So our final answer is going to be 0.1224 moles of oxygen. Let's take a look at our final example. In this example, we're converting from 10 grams of sodium chloride to grams of fluorine gas. So we're going to begin actually by finding out the molar mass for sodium chloride. So we have sodium, which is equal to 22.99 grams per mole from the periodic table. We have chloride, which is equal to 35.45 grams per mole from the periodic table. So we wind up in this case with a final amount for sodium chloride that is equal to 58.44 grams per mole. Next thing, before we go into our equations, let's balance our chemical reaction. We have 1 sodium, 1 sodium. We have 1 chlorine on the left, but 2 on the right. So we're going to need to convert this to a 2. We're going to convert the sodium fluoride now to a 2. And these will both end up being 1s. Now we can set up our equation beginning with our 10.00 grams of sodium chloride. Now, in this problem, we're going from grams to grams. That's a 3-step problem. So in the first step, we're going to go from grams to moles. In our second step, we're going to go from moles to moles. And then in our third step, we're going to go from moles back to grams. So to begin, I'm going to take that 58.44 grams of sodium chloride. We're going to put that on the bottom. That's equal to 1 mole of sodium chloride. In our second fraction, this is where we're going to use the mole ratios. So we have on the bottom 2 moles of sodium chloride. Just as a reminder, I'm going to turn that blue so you can see where we're using that. And then because in this case we're going to fluorine, notice how we don't even have to go across the arrow. We're going from one reactant to another. We have 1 mole of F2. I'm going to make that blue as well. Now, if you would like, and you don't have to do this, you can also show how the units cross out by highlighting them and holding down Shift, Alt, and then the number 5. That'll show how the units will cross out. So grams of NaCl cross out. Moles of NaCl also cross out. Right now we have moles of fluorine. We're trying to get to grams of fluorine. Fluorine itself has a molar mass of 19. Because we have F2, that's going to be a molar mass of 38. So in this case, we're going to have 38.00 grams of F2 for every 1 mole of F2. That again is just using the numbers from the balanced equation. We need to cross that out. So now we can cross out this unit, moles of F2 with moles of F2 here. And we're left with a unit of grams of F2. Typing all of this into the calculator. We have 10.00. We don't have to do anything with 1, so forget about that. Divided by 58.44. Again, we don't have to do anything with 1, but we do have to divide by 2. And then finally, we're going to multiply by 38.00. We get this answer. So I'm going to copy and paste a whole bunch of it, but we're only going to keep 4 significant figures. So 1, 2, 3, 4. Now behind this 1 is another 1. So this is not going to round up. So we're just going to cut that off. We have grams of F2. Okay, that brings us to the end of today's lesson. What I would like you to do is finish problems 4 through 13. So you have 10 problems for homework. Please let me know if you have any questions. And as always, I'll be available for office hours. So please stop by. Thanks, everyone. Have a great week.